Okay, so welcome back everyone. We continue with the third talk of today's session. The speaker is David Sauzin from CNRS, and he's going to talk about on resurgent series and their stability under multiplication and Moyal star product. David, please.
Thank you, Gergo. Let me first thank the organizers of this summary meeting for the opportunity to give this talk, and thank also all the organizers of this program of Isaac Newton Institute. So my goal today is to report on a joint work with Shanzong and Yong from Beijing on the Moyal star product. But this will require to review something about multiplication of formal series product before going to star product. And as you know, the Borel image of multiplication is convolution. So I have to review something about the convolution of endlessly continuable germs. And this is because the Borel image of this Moyal star product appears to be a kind of mixture of convolution and Hadamard product. And Hadamard product is a kind of multiplicative convolution. So this is my goal. So let me show you my references at the very end. So you see, I will discuss in the second part the content of these papers with Sun and Li. And of course, there is some overlap when we speak of convolution with this joint work with Shingo Kamimoto. There is an overlap with Shingo's talk of this morning or afternoon or evening, according to your own time zone. So let me start with definition and examples of resurgent series. This is ECAL first definition, 81. Here we fix in advance a set omega, closed and discrete, finite or infinite, and you fix a priori the location of singularities, of potential singularities. You say that phi hat is a holomorphic germ, so this is the notation for convergent power series in psi with positive radius of convergence identified with germs of holomorphic functions. So such phi hat is called omega continuable if one can follow its analytic continuation along any path starting in its disk of convergence and avoiding this set omega. So you see here is a path gamma starting from the disk of convergence and avoiding this set omega. The points of omega are marked by big dots. All such paths should be path of analytic continuation. So it's a subtle property of analytic continuation of phi hat. Obvious examples are meromorphic functions. You have a single valued holomorphic function outside isolated points. So when you avoid them, okay, analytic continuation is possible. Algebraic functions, you have a finite set of singular points, but possibly the analytic continuation is multi-valued. You see that this definition authorizes multi-valuedness. Another elementary example is holonomic functions, as we've heard in the previous talk by Frédéric Fauvet. So notice one thing. What about the origin itself? The principal branch, by definition, you see in my definition, it's holomorphic in a disk center at the origin. It's regular at the origin, but nothing prevents omega from containing the origin. This means that possibly when you go back to origin, you are in trouble. Here is a very elementary example we've already seen in Shingo's talk. So let me present it here just as a warm-up. So take this phi 1 hat. So clearly this phi 1 hat is convergent in the disk of radius 1. At the origin, for the principal branch, it's only an apparent singularity because the logarithm vanishes. So we have this disk of convergence of radius 1. But at 1, there is a singularity. And when you follow a path like that, and you turn around point 1, if you try to come back, then it's very possible that for the branch, now you see the singularity. It is no longer apparent. So this is why this function is omega continuable with omega containing 0 and 1. And you cannot do it with 1 alone. And the same is true for its primitive, and the primitive happens to be the classical dilogarithm function. Okay, let me show you an example related to the Stirling series. So here we are still with elementary case of a meromorphic function. So I'm speaking of a function mu hat now. Mu hat is this very concrete meromorphic function. And so again, at the origin, it's an apparent singularities, and since it is single valued, there will be never any singularity at the origin. The poles are located on non-zero multiple integer multiples of 2 pi I. So that is related to the Stirling series. How? The Laplace transform of that. So this is a germ in the psi plane. This is the Borel plane. It extends analytically in all directions except imaginary axis. So you can take the Laplace transform, the usual one, and what you get is the logarithm of the normalized gamma function. So gamma divided by the Stirling factor. And you go from one to the other by L0. The 0 here stands for the argument. So in direction 0, in the positive real direction, you take the Laplace transform, the usual one. And this brings you from mu hat to mu of z. And of course, as you know, there is an asymptotic expansion at infinity in the z variable, which is nothing but the formal Laplace transform of the Taylor series of mu hat, or vice versa. You can say that this Taylor series is the Borel transform, the formal Borel transform of mu tilde. Great. Let me show you another example, less well known. Let me consider the Lambert W function. So it's defined, W of x is a solution to this equation, but in fact the solution is multivalued. So there are two real branches defined for x between minus exponential minus 1 and 0 on this little negative interval. So let me call W0 and W minus 1 the real branches of this Lambert W function. Let me consider that difference evaluated at exponential minus 1 minus psi. So you may ask why, but well, let me do it. Now, you may know that the Lambert W function has a nice analytic continuation in the x variable. This minus exponential minus 1, this is a square root branch point, because this number is the only critical value of w exponential minus w attained at w equal to minus 1, the only critical point. So this, in the x variable, this is a singularity. 0 also is a singularity coming from the asymptotic value at infinity, but we won't reach 0 because we are using exponential of minus 1 minus psi. So you will never hit 0, but when psi is 0, for instance, you see that we have a singularity at the origin. Indeed, there is a Puiseux expansion with half integer powers, square root branching. But now when psi moves in the psi plane, if you go to 2 pi I, again, you are hitting the singular point. So this means that our germ lambda hat, so it's a slight generalization of what we were seeing before, because we have accepted a branching at the origin, but it's a mild singularity at the origin. But now we have this property of 2 pi I z continuability, meaning that you can follow the analytic continuation of lambda hat when psi moves from a disk, a punctured disk at the origin, in the complex plane, avoiding 2 pi I z. This way, x will avoid minus exponential minus 1. So this is an example of an omega continuable function with omega equal to 2 pi I z. And this is not an artificial example. In fact, if you apply Laplace transform, you go from lambda hat to the exponential of the previous one to the gamma function with, well, there is a slight difference with the normalization. There is this prefactor z to the minus 3/2. Okay, it's just a different normalization, but it's still gamma function divided by the Stirling factor. So what I'm saying here is that the exponential of the Stirling series up to this prefactor is resurgent in the sense that its Borel transform is the Puiseux expansion of an omega continuable function. And here you see there is a slight generalization in the sense that we accept at the origin a non-integer power, let's say c, here c is 1/2. It can be anything with a real part larger than -1, so that the germ is still integrable at the origin and the Laplace integral is still well defined. And of course, you have to accept to modify accordingly the definition of the Borel transform. Instead of dividing by the factorial, you divide by gamma function, which is well defined when k has positive real part. So these are two elementary examples of resurgent series in the sense that in the Borel plane, in the psi variable, this one is meromorphic. And this one is not meromorphic, it's multiple valued, but because it comes from the inversion of a nice function, it is still omega continuable with appropriate omega. So let me state this as a definition. So yes, it's a more general definition. It's Ecal 85, the third book on resurgent functions, preprint of Orsay, which was, let's say, explained very well in this book by Kandelberger, Nosmas, Pham in 93. So this is a more general definition now because we do not fix in advance the set omega. And here, well, I could refer you to Shingo Kamimoto's talk. So let me read it. Phi hat, a holomorphic germ at the origin, or maybe you have a power, or maybe you have a sum of, let's say, a Puiseux expansion, for instance, convergent. You say it will be endlessly continuable if for every L positive, there exists a finite set of points omega L to be avoided when you travel for a distance less than L. So a finite omega L such that one can follow the analytic continuation along any path of length less than L or at most L, starting in the disk of convergence and avoiding omega L, this finite set. It's finite, but of course, if you increase the length of your path, probably omega L will become richer and richer. So what you need here is to look at is the union of all these omega L without loss of generality. You can assume that it's an increasing union. And it's with that more general definition, the singular locus, the totality of all these possible singular points may very well be dense in the complex plane. It may accumulate in some parts of the complex plane, but you only see finitely many obstacles at a time. And this is needed in particular in the WKB case. And it's a generalization of the previous definition, because in the previous definition, we were fixing a priori, a closed discrete set, possibly infinite. But when you take the intersection of that set with the disk, the closed disk of radius L, you have a family of finite sets, and you can check the definition. So let me show you a picture. I have prepared something like that. So let's say here, this was a path of length L. So for this path of length L, we had to avoid a number of singular points which were drawn by the big dots. And now let's suppose that we are trying to go farther. So now we extend our path. It has a length L prime, and associated with L prime, there will be a new set omega L prime, possibly larger. So the question is, the fact is that you need to avoid more points. So maybe in this set omega L prime, there are more points to be avoided. Maybe points which were previously allowed are no longer allowed. Maybe now for longer distances, they have become obstacles. So now this would be a longer path of analytic continuation, but be careful that maybe you have many more obstacles. So this is the idea that the set of obstacles can be much richer. It can accumulate. Well, one image, you can have a relativistic analogy. Imagine your path is traveling with unit speed, and your singularities, in fact, are not in the space, they are in space-time. So here we are saying that the singularities occur after a certain time, and once they have occurred, they will stay forever. But initially, when with small length, if you don't wait for a very long time, you see only finitely many obstacles. But if you wait forever, then in space-time, and afterward you project on space, maybe you see a dense set of singularities. So there is no omega closed and discrete, not anymore. So this is why the second definition is definitely more general. Now let me go to the definition of a resurgent series. It will be any formal series whose formal Borel transform is an endlessly continuable germ. And you see the classical triangle. So a resurgent function, it's not safe to call the function in the Xi plane resurgent functions because it can lead to confusion. So let me say that, to be very strict, we started in the Xi plane and we define endlessly continuable functions. By Borel transform or inverse Borel transform, we define resurgent series. So those series whose Borel images are endlessly continuable. And now a resurgent function is something you obtain by summation. So typically by Laplace, some Laplace integral, or maybe some generalization. We heard about Ekal's averages a moment ago. So some suitable generalization of Borel Laplace summation. So which means that now you can say you start from phi tilde, you compute its Borel image, it's endlessly continuable. It means we are in the resurgent world. And now hopefully you can apply Laplace or Laplace modified by Ekal, and you get a function in the Z variable in some sector, typically in a large sector. And this function is called the resurgent function and has an asymptotic expansion at infinity, which is nothing but phi tilde of Z. So the initial divergent series appears as the asymptotic expansion of this function, at least in a sector at infinity. Z is at infinity. This is why our powers were always negative. I suppose most of this is familiar to you. So now let me review multiplication, convolution, and Hadamard product as a preparation for star products. And let me start with this very important theorem. Resurgent series are stable under multiplication and nonlinear operations. For instance, substitution into a convergent power series. So this was claimed by Ekal at the very beginning of the theory. For a detailed proof in the framework I have presented You can find details in the paper of mine, especially a joint work with Shingo Kamimoto. If we use the definition of endless continuability using this mechanism of discrete filter sets. So this is really what we heard in Shingo Kamimoto's talk. And let me give an example. You remember the exponential of the Stirling series. We had a formula for its Borel transform. It was lambda tilde. But in fact, we knew in advance that the exponential had to be resurgent. I mean, it's a theorem that whenever you have mu tilde, the resurgent series, its exponential has to be resurgent. What was exceptional in the case of Stirling series is that there was a closed formula for the Borel transform of the exponential in terms of the Lambert W function. That was not expected from any general theory. But the general theory tells you that resurgence is a robust property. You do not destroy it by exponentiation, by solving functional equations for implicit function, etc. Contrarily to weaker properties, like we said at the beginning, meromorphic functions are example of endlessly continuable functions. So we could have said, okay, an easier definition of resurgence is when the Borel transform is meromorphic. But then as soon as you do a product, in the Borel plane, you lose the single valuedness. So it's not robust at all. And the same with algebraic functions. Holonomic functions have some good stability properties, which we heard in the previous talk, but not as good as the set of all resurgent series. Let me give another example, which I find quite striking. You see here, I say this robustness, this stability property explains why resurgent series are so abundant in nature. It's because what I mean here is, take this example. So this is an example we heard about, for instance, yesterday in Karen Yeat's talk. And it's a story which started with David Broadhurst and Dirk Reimer years ago. And there was a contribution very interesting by Misha Borinsky. And there is a more recent paper by Borinsky and Dune. They deal with, let me simplify things, and let me be very down to earth. Let's consider C of X, a power series. So here we are in non-negative integer powers of X at the origin, solution of that equation. So it's a nonlinear ODE. And the question is, how can you prove that the solution, the unique formal series solution to that, is resurgent? So here the resurgence variable, the critical time, is 1 over X. Well, here is the trick I learned from these papers. Consider another equation much simpler, 2x squared di over dx, I is the new unknown, plus x minus 1i equals to minus 1. So you see it's a linear ODE, inhomogeneous linear ODE. So no surprise. I mean, it's the solution has to be holonomic. The coefficients are polynomial. And in fact, it's very explicit. This auxiliary equation has a very concrete solution. It's a generating series of the double factorials. And the Borel transform in the critical time is just this power minus 1/2 of minus 1 of 1 minus 2 psi. So it's this, with this normalization, it's algebraic. Hence, I is resurgent. Okay, this is first elementary example of continuability. So more precisely, I is has a Borel transform, which is omega continuable, where omega is essentially 1/2. The only singularity is psi is 1/2. Great. How does this help? It so happens that the solution to the nonlinear ODE is obtained from the solution to the linear ODE by this strange operation. Take I minus 1, compose it, this is composition with H, the composition inverse of xi squared. It's a fact, you can check that exercise. you have EI here defined by this equation, compute xi squared, consider this as a change of variable, compute the inverse, compose I minus 1 with the inverse, and you get C. Great. This is great because I is resurgent. Écart tells you I square must be resurgent too. It's the Borel transform is no longer algebraic, but you don't care. The functional inverse of a resurgent series is resurgent. That's part of the nonlinear operations which are covered by Écart's theorem. So H is resurgent. And now this is the composition of I minus 1 resurgent with H resurgent. It has to be resurgent. And you can go even farther, as we reviewed that in the previous talk. When you have singularities in the Borel plane, you want to use alien calculus, alien operators defined by Écart, which behave nicely with respect to multiplication and also with respect to nonlinear operations. For instance, when you compose resurgent series, you have the alien chain rule to compute alien derivatives. So in this situation, you can compute alien derivatives of C just because you know explicitly all you want about the Borel transform of I. And as you know, this Écart's alien calculus is related to the Stokes phenomenon. Well, this is not exactly my subject today. So my subject is rather to explain why this theorem holds, and the proof of the theorem requires the analysis of the counterpart of multiplication. This is the least you need. In nonlinear operation, you start with multiplication and then any multiplication of any number of factors. And then if you substitute, for instance, several power series, resurgent series inside a multivariate convergence expansion, you will need to deal with many multiplications. So the least you need is convolution product, because this is the counterpart of Borel. I mean, this is written here, you see. The convolution of f and g can be defined as the Borel image of the product of the inverse Borel images, and there is an integral formula. So very nice. So when you want to prove, let's imagine we want to prove a little part of Écart's theorem. We want to prove that just the first line, resurgent series are stable under multiplication. This is equivalent to saying that endlessly continuable functions are stable under convolution. This is just a tautology. So how would you do that? We now review the basic arguments behind this statement. So the question is, how will we follow the analytic continuation of the convolution of two endlessly continuable functions? So suppose f and g satisfy the property we have said. What can you do with f star g? Similar arguments will allow us to handle the Hadamard product of endlessly continuable functions. So this means that we will be able to prove a resurgent version of the famous Hadamard multiplication theorem. So you see, today's talk is very in the spirit of 19th century mathematics. And in fact, we need that as a preparation for the study of the Moyal star product of resurgent series. So we've defined convolution. Let me define Hadamard product. This is the pedestrian definition in terms of Taylor series. So f and g, let's imagine they are in the Borel plane, convergent expansions, for the sake of simplicity, only integer powers. So then you multiply the coefficients. I mean, imagine you are a bad student and you were asked to compute the product and you forgot the rule for the Cauchy product, the product of series, and you write that. Well, if you are Hadamard, it's not a mistake. You have invented a new operation. And in fact, it's great because there is an integral formula. So the same way we have an integral formula for the convolution product, we have here a kind of multiplicative convolution, you see, and the integration is on a circle. C rho is the anti-clockwise circle of radius rho. So you need to take rho small enough so that you are using f in its disk of convergence. But then accordingly, you need to take psi small enough so that psi over zeta, when zeta has modulus rho, should be in the disk of convergence of G. So the modulus of psi should be less than rho times the radius of convergence of G. So rho should be taken small enough, but not too small, because if not, if you take it too small, then the formula is valid for a very, very tiny disk. Great. So now let me devote a bit of time to explain this simpler theorem. So this, with respect to Ekal theorem about all nonlinear operations that you need, for instance, if you want to implement the argument I mentioned about the generating series for chord diagrams, you would need really composition, etc. But well, let's be content with multiplication and Hadamard product. Well, let's say we stick to the Borel plane. So we are interested in Hadamard product and convolution. So for the Hadamard product, the statement is that if f is a continuable, so here I return to the 1981 definition, the simplest one. You fix in advance the set of singularities. So I suppose that f has, in the Borel plane, analytic continuation wherever provided you avoid A, G wherever provided you avoid B. Then so is the case for f Hadamard G when you avoid omega 1. The points of omega 1 are the origin and all possible products of points of A and B. Well, this is a resurgent version of the famous Hadamard multiplication theorem. The singular points are just products of singular points. Well, in fact, the classical Hadamard theorem is concerned with the principal branch, or not only, but well, there is a variant with spiraling domains, but essentially it's a story happening with the principal branch. And here, what we want to deal with is really the multi-valued analytic continuation. We want to explore the Riemann surface of the Hadamard product with these assumptions. I mean, we restrict our attention to those continuable functions. And the classical statement for the convolution is that it is omega 2 continuable, where omega 2 is the union of points of A, points of B, and sums of a point of A and a point of B. So now, well, it's what I've said is written here. So, I mean, this part I, we prove it in a separate article, a very short paper with Shanzong and Yong. It's a refinement of the statement on the principal branch given by Hadamard and Borel in 1898. It's a beautiful story. Hadamard had announced his theorem in a note, a short paper, short announcement, and then he gave he published a full paper. And Emile Borel was immediately fascinated by that operation, and immediately he started to work. And the same year as Hadamard, he published his own version of the theorem. And I mean, they are very close one to the other. And we will say something about Borel's paper here, because he says something about the analytic continuation to other sheets. So this way we will discuss part I of this theorem, and you will see that part 2I, which is super classical now, but I mean, it's in Ekal, it's in Kandelberger and Osmas-Pham, but in fact, it comes from Borel's idea in a sense. So first manifestation of the fact that Borel, whatever he says, Borel thinks of the analytic continuation to the other sheets, because he mentions the necessity of including the origin here. I mean, you see, in our theorem, we need the origin in omega 1. Which means that omega origin should be avoided. Not initially, I mean, the Hadamard product is regular at the origin. So the principal branch has no problem at the origin. But if you travel on its Riemann surface and you come back to the origin, possibly at the origin, there is a singularity. Borel mentions it in his paper and gives credit to Lindelöf for that point. And here is a very simple example. minus logarithm of 1 minus psi. This is omega continuable, or sorry, this is A continuable with A reduced to the point 1. Okay? What about F Hadamard F? Well, compute it and you will see F Hadamard F, this is the dilogarithm. The dilogarithm is omega continuable, but omega must contain the origin as well. This is the example we've seen at the beginning. When you return to the disk of convergence, once you have turned around point 1, you see a singularity at the origin that you did not see on the principal branch. Here is the basic idea to prove this theorem, part I, let's say. And really, we follow Borel's ideas, Borel's instructions. So here is my own translation of Borel's paper. It's published in French in 1898. This expression of F Hadamard G, so he refers to the integral formula written in this peculiar way. You see, F Hadamard G is an integral on the circle of dx over 2 pi I x, f of 1 over x, g of psi x, and psi is the argument. So psi is the variable with respect to which you want to follow analytic continuation. So you start with integration on a circle. And as we said, this formula is valid for psi of modulus small enough. This expression, says Borel, stays valid if one deforms the integration contour without letting it cross any singular point of the integrand. And so what he's saying is that use Cauchy theorem. I mean, this formula is valid with the circle, but certainly you can deform the circle, apply some homotopy, and you have a new contour. And well, if your deformation has not crossed any singular point of the integrand, so that is to say with respect to x, then you are safe. Cauchy theorem guarantees it's the same formula. You are speaking of the same number, psi being fixed. But now here is a subtlety. Psi is the variable, it's not fixed. So once you have modified the contour having been fixed in some arbitrary manner, one obtains the analytic continuation of F Hadamard G by moving psi. So now psi is no longer fixed. So psi can move in the plane provided the singular points of the integrand do not cross the integration contour. It sounds like the same sentence, but he's saying something differently. He's saying that now the contour is fixed, but it's no longer a circle. So the domain of validity of this formula is no longer a disk. It's a domain in which you can move psi, well, provided the singularities of the integrand do not hit the path. Well, I mean, when psi moves, the singularities of the integrand move, and they should not hit the new contour. So I said that Hadamard and Borel were concerned with the principal branch, and throughout his paper, Borel seems to keep in mind the possibility of going to the non-principal sheets and dealing with multi-valued analytic continuation, yet reluctantly slow. Since when he explicitly mentions that possibility, one could try to go to different sheets. He tends to recommend to discard it, and he writes, it seems to us useless to insist on that latter point. One would be led to complicated statements. Well, and this is what Ekal accomplished. I mean, he gave an elegant theory which contains these seemingly complicated statements. And I mean, after all, they are not that complicated. Well, I say that Borel is reluctant. However, he puts in a footnote an idea that has been successfully adapted to study analytic continuation of convolution, F star G, so the additive version of convolution. And the same idea can be, was given by Borel for the multiplicative convolution. So let's view this footnote. I have translated it for you. So what I'm saying is that Borel in 1888 gave ideas that have been adapted successfully by Ekal, and Candelberger and Osmasfam follow Ekal for that point, to prove part 2i. You remember part 2i of the theorem, when you convolve two functions, well, you just have to avoid these points. So now we return to Hadamard product and let us follow Borel. It's very beautiful. So Borel writes in French, let us conceive the closed contour C as a flexible extensible thread. The singular points of f of 1 over x, you conceive them as pins stuck into the plane. So pins, well, where are these pins? Singular point of f of 1 over x, it's when 1 over x is alpha, any singular point of f. So it means x is 1 over alpha. And also you have 1 over x here, you see. So we should also stick a pin at the origin. So we have pins stuck at those points, the points of the form 1 over alpha, where alpha is any singular point of f, and the origin. Let us conceive the singular points of G of psi x as pins that travel as psi moves. Indeed, if G is singular at a point beta, this means that G of psi x is singular when x is beta over psi, and when psi moves, beta over psi moves, clearly. And then Borel says it is necessary and sufficient that the thread always part the two systems of pins. In a minute, we'll see a picture. So the condition is they should be different. Now, this will always be possible by means of a suitable deformation if, while traveling, the second pins never come to hit the first ones. The thread may acquire a very complicated force, but this is harmless. I think I have an explanation here. So what he's saying is that the first system of pins, 1 over alpha or 0, should never hit the 1 over alpha should not coincide with beta over psi. And also beta over psi should never be 0. So this means that psi should never be in the set alpha dot beta, and psi should never be 0 because we would be in trouble. Yes, something like that. So this is Borel's explanation for Hadamard product, and let's go now quickly to convolution product. It's the same story. You have an integrand which is singular with respect to psi1 when psi1 is one of the fixed singularities of f, or when psi minus psi1 is one of the betas. So you see here now, well, the closed contour, it's not a circle that we should deform. The initial contour is a line segment. So the analytic continuation of f convolution G along a path gamma, imagine you are following a path gamma parameterized by S, it will be given by an integral on a new contour HS of the same thing. You see, G gamma of S is just psi. Gamma of S is just psi. Well, provided HS is a suitable deformation of the line segment. In particular, I should go from the origin to gamma of S. Now, what are the conditions? This HS should avoid the points alpha because we have f of psi1. It should avoid gamma of S minus beta because gamma of S minus psi1 should not be equal to beta. So these two systems of pins should not collide. This means that psi, which is gamma of S, should not belong to the set, the union of alpha and beta. Okay, let me illustrate all this with a picture. In the case of the convolution, so now I'm looking at that formula. I have my path gamma, You see, this is the gamma I want to use. And these alpha, the first dots here are the dots, the pins alpha. And well, if you view them like that, it means that at each point alpha and also at the origin, by the way, you have a pin. And now you have your extensible thread starting from, let's say, gamma of 0. Initially, gamma of 0 is very close to the origin. So you can use a line segment, no problem. And even for that gamma of S, I can still use a line segment. You see my thread here between the origin and psi is still parting the first system of pins, the alphas, and the second system of pins, the psi minus betas. Psi minus beta, psi minus 0, psi minus beta is here. Yeah. Okay, but now I would like to follow the path from gamma of S until gamma of S prime. So now you see that my thread will enter between the alphas, and the fixed pins will push my thread. So I will get something like this. When I try to do that, my thread is deformed because of the fixed pins, and the moving pins are pushing the thread in between. So it's like that. But well, Borel's recipe is very clear. So we can go on now. Now we want to go from psi prime upward toward psi second. Well, it's possible. The thread accepts to be deformed this way because you see my psi second is not a sum alpha plus beta. That would be a trouble, as we have explained. Psi, which is gamma of S, should never be of that form, alpha plus beta. And we can go on like this. And yes, we can easily obtain complicated shapes for the final path. So this is Borel's great footnote. Our contribution, I worked on that for the convolution, and we worked on that for the Hadamard product with Shanzong and Yong. Our contribution was to give a formula for the deformation. So you see, it's all about constructing HS when S goes from 0 to 1. So it's deforming a path. So can we construct explicitly the deformation when psi moves in the complex plane without meeting these points? We do it by applying to the initial contour a continuous family of homeomorphisms. So S is moving, and each psi S is a homeomorphism. We apply it to the initial path. Of course, this family of homeomorphisms must satisfy certain properties. And the point is that how do you construct a family of homeomorphisms? A method I learned from Kandelberger and Nussbaum is to use the flow at time S of an explicit non-autonomous vector field. This is why one could call this method the vector field method. We try to cook up a non-autonomous vector field depending on the time is S, the time parameter is S. It depends very much on the path gamma that you want to follow. And in terms of this path, we will cook up a vector field whose flow at time S gives you one possible deformation, satisfying all what you need. So it's not only academic. I mean, after all, you could believe Borel's idea, and I mean, Ekal's paper is fine for that point, as well as Kandelberger and Nussbaum. But the benefit of such a detailed, rigorous proof relying on an explicit vector field is that it allows for quantitative estimates, which in turn can be adapted to prove fully in all details Ekal theorem on the stability of the space of resurgent series under nonlinear operations, and not only multiplication of two factors. So let me show you how we do that in the case of Hadamard product, because we need it in few minutes. So we are given a path which avoids the set omega 1. You remember omega 1 points of the form products, alpha, beta, or the origin. And we wish to construct a continuous family of Lipschitz homeomorphisms such that when S is 0, you do nothing. And when S is between 0 and 1, well, I will impose these conditions. Condition 1, I will impose that psi S fixes the points of A and the origin. And when you apply psi S to gamma 0 over beta, you find gamma of S over beta. Why am I requiring that? It's because this way, this formula will hold true. This way, you take the same integrand, but you integrate on these deformed parts. You see, we have applied psi S to the initial circle 0, and I claim that this gives you the analytic continuation of the Hadamard product. Well, this notation means continuation along gamma until time S. So this is a function, this is a value at gamma of S. Well, and not only, I mean, psi can be anything close enough to gamma of S. So the question now is, well, I mean, I claim that condition 1 was sufficient. Here is the proof. If condition 1 is fulfilled, then it's guaranteed that when zeta is imaged by psi S of a point of C, zeta is not on A and is not at the origin, because for that to be true, zeta would have needed to be at alpha or at the origin to start with, and it's not the case. I mean, when zeta 0, the point of which zeta is the image, zeta v0 is not at the origin, is not on A, hence its image is not at 0 or at A. Similarly, if zeta 0 is on the circle, then gamma of 0 over zeta 0, I mean, this is the moving pin at time 0. And we have said the moving pin at time 0 is not one of the betas. This condition 1 will imply that its image, which is gamma of S over psi S of zeta 0, so this is psi over zeta, this is psi over zeta. So psi over zeta is not in B, because if it would have been equal to beta, then it would have meant that we started with zeta 0 in B. So therefore, this deformed contour avoids the singular fixed points 0 or alpha and the moving singular points. And how do you construct a family of homeomorphisms which satisfy condition 1? One possibility is to use the flow map between time 0 and time S for this very concrete non-autonomous vector field. So I'm sorry, it's a little bit technical, but it's simple. This formula is well defined. You can check it. Eta, you see, gamma is the path, so gamma prime is the velocity, zeta over gamma of t, it's a complex number, and eta, it's a Lipschitz function that we have chosen such that it vanishes when on every point of A, except the origin, and it takes value 1 on those points. But you see, this condition is saying that eta is separating the point of A from the point, the moving singular points. And well, this is possible because we have said I mean, of t is not of the form alpha times beta or 0. So these numbers are all positive, and by compactness, this infimum is positive. So this eta function exists, and then you can check easily condition 1 is fulfilled. I mean, this vector field is fixed, for instance, fixes the points of A. Okay, that's an exercise now. Good. So this is the solution to the, I mean, this is the statement of the exercise. Check that condition 1 are fulfilled. Let me give a few details for the convolution. Well, the only detail I give here is that there is another formula for the vector field of the same flavor, and it will give you a flow which satisfies what we need to have the property. So, final part of my talk, I dwelt on convolution, on Hadamard product. All this was a prelude to Moyal star product and algebro-resurgent series. So here is a snapshot of the last 2 or 3 slides. The Borel transform with respect to t. So now, instead of z at infinity, we'll have t, which is I times the Planck constant. So t is infinitesimally small. And we want to consider the Borel transform of a Moyal star product. You will see what it is. It can be written in terms of the Borel transforms of each factor, f and g, but now f depends on psi, the Borel variable, and qp, the phase space variables, because we are doing deformation quantization. So we have a phase space with variables, 2D variables, let's say, q and p's. The formula which will get what in the Borel plane appears to be a mixture of convolution with respect to psi and Hadamard product. It will involve these kind of factors. So it's more complicated because we have more variables. And to handle analytic continuation in such a many variable context, we need to put restrictions on the singular locus of f and g. And for that part, we follow this precursor article published by Garay, de Goursac, and Van Straten in Annals of Physics in 2014. They introduced this definition of algebro-resurgence with a view to not the Moyal, the standard star product. So the idea now is that since our functions in the Borel plane also depend on the phase space variables, QP, we will impose a condition on analytic continuation away from a subset of C3, at least 3 variables, or maybe 2n+1 complex variables. So the condition is algebro-resurgence, meaning analytic continuation is possible away from a proper algebraic subvariety of C3. So this is the definition of the Moyal star product. So you start with a Poisson structure with constant coefficients. So you work in some open subset of D, and D will be 2n, because if your Poisson structure has constant coefficients, even if it is degenerate, you can find Liouville coordinates. So this is the Poisson bivector, the wedge product of 2 vector fields. And this is the Poisson bidifferential operator. And I mean, this is the usual Poisson bracket of classical mechanics. And if you write things in this way, the Moyal star product is obtained by exponentiating t over 2 times the Poisson bidifferential operator. So you get this formula in containing differentiations with respect to all variables. And what's nice with this formula, I mean, it's deformation quantization. It's a deformation of the product. You see that it starts with the product, and then you have this t, which is infinitesimally small, and it's a deformation in the direction of the Poisson bracket. You see that the commutator of the Moyal star product is exactly the Poisson bracket at order 1. By a linear change of variables, you can reduce the situation to the case of the standard Poisson structure. I mean, here it is in 1 degree of freedom. So the formula simplifies a little bit. Here is a very simple example. This first function is 1 over 1 minus p. This is a function on the phase space with a singularity at 1. The second function is anything not dependent on t, the deformation parameter. But because of all these repeated differentiations, you get something which is non-trivial and which is divergent. The k derivatives here are not compensated by any factorial. So this is factorially divergent in general. So what can we do? We use this modified Borel transform. We divide by the factorial to restore convergence. And you see that in this particular example, yes, it works. I mean, when you divide by the factorials, you restore convergence, and you even have a very explicit formula, finite radius of convergence, and you can say something about the analytic continuation if you know something about the analytic continuation of G. So what is the general theorem behind that? Here it is. So you define the set of algebro-resurgent germs in R variables as the set of phi hat functions of R variables such that there exists a proper algebraic subvariety of CR such that this phi hat, which is convergent in a polydisk centered at the origin, has analytic continuation along any path which avoids this proper algebraic subvariety. Of course, the path has initial starting point close enough to the origin. And then the theorem is that, algebro-resurgent series, a formal series in R variables, but the first variable is T, the deformation parameter, the Planck constant. And you want the Borel transform with respect to the first variable to be algebro-resurgent germ. And the theorem is that for any constant coefficient Poisson structure in D variables, the Moyal star product of two algebro-resurgent series is again algebro-resurgent. So I think my time is over, so I will stop there. The proof, I mean, you just need to study the Borel image of the Moyal star product. So what is it? The Borel image is this circled star product, which has a nice integral formula. So the point is that you have integral formulas in the Borel plane, which look like a mixture of multiplicative convolution and additive convolution, so you can adapt Borel's ideas. Thank you for your attention.
Thank you very much, David. I see there are two questions, so maybe we can start with David.
Thank you, David, for this absolutely wonderful talk. You've helped me understand the appearance of the Lambert W function in the non-perturbative result of Michael Burinsky and Gerald Dunn. But there we're starting off with essentially combinatoric problem. Remarkably, it also is the non-perturbative solution to a problem studied by Reymar Vulkenhaar and Eric Panzer, which is non-commutative phi to the fourth theory with a Moyal product where the perturbation series is polylogarithmic. But they have solved that non-perturbatively. So if you're really interested in Lambert W, please look up the paper with Panzer and Vulkenhaar, which says Lambert W solves phi to the fourth theory in Moyal space. That seems to resonate with your talk somewhat.
Oh, I will. Thank you for the reference. Maybe you can send me the precise reference. But anyway, Vulkenhaar and Panzer, Eric Panzer. Okay, thank you.
Okay, Charlotte.
Oh, yeah. Hi, David. This is Saleh Tanvir. I'm a bit confused about endless continuation definition that you made for the following reason. If your definition of endless continuation will not disallow the following picture, which is as I go on a ray, I have the singularity locations bunch up as I go farther and farther away.
Bunch up, what do you mean?
They get closer and closer.
Okay.
As I go farther and farther towards infinity. Because the length is getting larger.
Yes.
So the separation between singularities are getting smaller and smaller.
Yes.
Under those conditions, how would you define École, Borel-Laplace transform using École averaging? Because I mean, if you have singularities which are getting arbitrarily close to each other, do you still?
I don't see any difficulty even in that case, because the path that you will be using have finite length, and these length is bounded
No,
a priori.
when you take the Laplace transform, I assume that this notion allows you to do to Borel sum, or is it not?
I never said such a thing. I never claimed anything about the possibility of applying Ekal's average. I said that ideally, what you would like to check, that one, your function is endlessly continuable, and then you didn't learn in vain Ekal's theory. And second, you would like to be able to apply some kind of Laplace summation. It might be the case that you are not able to apply it, and then okay, then you have to find another idea. But the general theory, by definition, so to speak, says that if you can do that, then such and such property will happen. But it's difficult to guarantee in advance that will be possible. So, in a sense, this is a little bit what we are aiming at in various papers you can find in the literature. For instance, this study is to say, if you have been able to prove endless continuability for the factors, then you can prove it for their product, for their star product. This is guaranteed. Then you would need another study to say under which conditions the possibility of applying Ekal's average is guaranteed. And there are situations where that occurs when you study certain equations, differential equations, difference equations, but I am not aware of any situation where we have this idea of singularities with interspace smaller and smaller. So you have a point there. I mean, maybe it's difficult to find a situation where you can have both phenomena simultaneously, but I'm not an expert in Ekal's averaging.
Okay, can I ask a second question, a quick one? Are you aware of the first order Chazy's equation? When you do analytic continuation, this is a first order equation which has a chaotic singularity as you go over to different Riemann sheets.
I heard about it because I heard talks by Ovidiu, for instance.
Okay, so that seems to fit in what you were saying before. As you go farther and farther out in terms of changing the length of analytic continuation, you end up with basically singularities filling up the whole spaces.
I mean, in that case, it's even worse because you have natural boundaries.
Okay.
So that falls in a completely different category. Maybe you need a Carl's other type of analytic continuation through natural boundaries. But that's a more complicated business. Yeah.
Maybe you need cohesiveness or something like that.
Yeah.
It's a state order.
Yeah, that's.
Yeah, I'm afraid so. Okay.
All right.
Okay, Ovidiu.
Okay. Yeah, we are running a bit out of time, but I had 3 short comments. First of all, I find this idea of that explicit deformation extremely nice and interesting. Actually, that you find that flow that implements what Carl sort of used already in his books, but indeed you can use it to do all sorts of estimates. The second one, I think these 2 types of continuability, the Hadamard product and the convolution, are linked in a deeper way through the Fourier duality between the product, in this case of coefficients, and convolution. So if you do an exponential map, I think you get the one from the other. You see, I mean, I'm pretty sure something like this must hold. That doesn't diminish the beauty of your analysis, of course.
Yes,
and third, go ahead.
On that point, I refer you to recent preprints by Ricardo Perez Marco about Hadamard product and what he calls any product. he has investigated the nature of the singularities that you find at the boundary of the principal sheet. But I must say that I tried to find a direct connection and I did not. So maybe it's possible.
Yeah, I think we could talk about it. I mean, I did need something quite similar, and the connection is I'm pretty sure I remember correctly that is there. And the third one is a bit random. Yeah,
I wanted just to advertise the paper by Marco. You see, it's very recent too. Yeah, and your third point, yes?
Right. Yeah, the third point is about that interesting ODE that you mentioned at the beginning that can be linearized. I think that this fits in with the theory of Painlevé. It's a first order ODE in his class, so it must be solvable either in closed form or in terms of special functions. So therefore, it must admit linearization. So the fact that there is such a transformation is almost a priori guaranteed by the theory of Poincaré. So that's how I see it. And probably I'll stop here because we're running short of time, and here we are getting a storm
Theory
that's
of
pretty dangerous.
Painlevé.
So yeah, the theory of Painlevé. We can discuss that too. It's so deep, and it's fantastic what he did.
Here, what is the connection? I mean, are you connecting that with what we said about the generating series for chord diagrams and the possibility of going from a nonlinear equation to a linear equation, or
to a linear equation, exactly. Yeah. So this kind of first order and second order equations, if they are integrable, and they should be integrable, they must be linearizable. So there must be such a transformation.
We must talk about
but
that.
That's a hunch. We can discuss in detail. And
I think I have the same kind of hunch, so I would very much like to discuss it with you.
I may be wrong, but I think it should be right.
Okay.
All right. So that's I'll kind of stop here with this. Yeah, I'm saying that there is a storm. I hope it doesn't kill my talk. I mean, it's an ugly storm coming here. Okay.